In this problem, we're going to be finding the complex square roots of a complex number, writing them in both polar and rectangular form, and then plotting them on this coordinate plane. So again, I'm focusing on square roots right here, and what that means is that n takes the value 2. You'll notice I have Moivre's theorem right here for roots, so I'm replacing all the n's with the number 2 in this theorem, even this little piddly one over here, so that's a square root of r. And now we can work through the problem. So first thing I need to do is rewrite z from rectangular form, as it is right here, into polar form, and that means I need to know the modulus and the argument. So the modulus z equals, well, remember what that is. It's the square root of real squared plus the imaginary squared, which if you work, we should have had practice at this by now, right? We should know how to do this. But if you work through that, you're going to get, let's see, negative 2 squared, that's going to be 4, 2 radical 3 squared, that's going to be 12, so we get square root of 16. Great, 4. So 4 is the radius of this point, and now we need to find the argument, because the argument is going to fit into these trig functions right here. I sine, and that angle will go right there. So if you take the argument, theta, that's equal to the arctangent, or the inverse tangent, of the imaginary part over the real part. Now the imaginary part over the real part should be pretty simple to see. So I'm writing over my graph here. But we have, that's going to come out to be negative root 3. So where is the tangent equal to negative root 3 on the unit circle? Well, there's two places. One is 2 pi over 3, and the other is 5 pi over 3, if you remember your unit circle values. And one of these is appropriate, one of them is not. If you look at your rectangular coordinates, this says left and up, right? Negative real, positive imaginary. That's left and up, that means quadrant 2. That means here we go, there's our angle. 5 pi over 3 is not for us. Okay, so this is going to be 2 pi over 3 for each of these. Little cheat for you guys who are watching the video. See the graph? It has the polar form graphed for you. So if you want, you can just look at this thing and say, oh, r equals 4 right there. Oh, look at that, 2 pi over 3, here's my angle. But it's useful to know how to come up with these things, because when you're in a test, they usually don't give you a nice hint like this. So now we're moving on. How do we actually find the roots? I've got the Moivre's theorem right up here. Okay, so we're going to use this thing. W0, well, that's for k equals 0, this very first root. So I plug k equals 0 into this thing. Well, first of all, the square root of r is easy. That's just the square root of 2. So each of these is going to have a square root of 4. Each of those is going to have 2 times something up front. And all I'm really asking is, what's the angle? Once you know the modulus, all that's left is to find the angle, and we'll have complete polar forms. Okay, so let me write those in here. Blah, 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 blah. Okay. So the angle of the original complex number was 2 pi over 3. And when we square root, we divide that by 2. So you get 1 pi over 3. This one's always easy to find. Just divide it by whatever the power is. So pi over 3, if I plot it on my graph, is going to look like this. There's my dot. Here's my line connecting it to the origin. I've now plotted my first root, W0. Now the second root is just going to be the first one plus how much? Well, see this part of the theorem? Plus 2 pi k over 2. That means every time, whether k is 1, 2, it doesn't go much higher than 0 and 1, but every time you add 2 pi divided by 2. That's pi. So we're adding a full 180 degrees, and we're going to get ourselves over here at this next one. This is going to be W1. So there's my plus pi, just to be real clear. And that's going to land me at 4 pi over 3. So we're done with the polar form. This stuff really is not too hard once you see the patterns and the symmetries. Now, an interesting question is, well, how do you know we stop at W1? What about W2, W3, and so on? Well, go ahead and try it out. See what happens. Just add another pi. The formula says keep adding pi's, right? So let's go ahead and do that. Add another pi. See what we get. Whoop. Look at that. We just found W2, and it's exactly the same as W0. So that's why there's only 2 square roots, because as you work your way around the complex coordinate plane, you end up repeating yourself. Now you can convert these to radical form pretty easily just by saying, what's cosine pi over 3? 1/2 times 2. Okay, great. That's going to be 1. And what's sine of pi over 3? That's radical 3 over 2 times 2. That'll give you a radical 3i. Okay? And likewise for the other one.